Hello everybody. Today I will show our recent results on the effect of different torques on the current-driven Skyrmion motion in antiferromagnets. I will start from the definition of magnetic Skyrmions, show the expression of spin transfer torque and spin orbit torque from the spinel effect, and focus on the Skyrmion Racetrack memory applications by showing the motion inside the antiferromagnet as well as in antiferromagnet, and finally some perspective and conclusions. Magnetic Skyrmions are topologically protected magnetization configuration characterized by an integer Skyrmion number. In the standard way, they are obtained in system with autoplane is the axis of the magnetization and in presence of a sufficiently large Jealousy Skyrmion interaction. We can deal with a variety of topological textures depending on the geometry, the material parameters, as well as the easy axis of the magnetization. But for the purpose of this presentation, we will focus on nil Skyrmions, and therefore, in the ideal case, we focus on a thin ferromagnetic layer in contact with the material characterized by large spin-orbit coupling, such as heavy metal, platinum, tungsten, and so on. And here is an example of the magnetization of the nil Skyrmion. Of course, we have a core in the autoplane direction and a circular domain wall where the magnetization is in plane and pointing outward or inward according to the sign of the DMI. The Skyrmions can be moved by the spin transfer torque as for domain walls. In this case, this is the expression of the spin transfer torque. I want to point out that this is made of two terms. One is the adiabatic term and the other one is the non-adiabatic term. And this torque is effective when there is a variation of the magnetization in the ferromagnet. On the other hand, we can also move Skyrmions with the spinel effect, spin orbit torque from the spinel effect. In this case, the spin polarized current is intrinsically generated into the heavy metal, and this spin polarized current is then absorbed by the ferromagnet, and it exerts a torque onto the magnetization vector. The type of torque is a damping-like or Stronczewski-like torque, and in this case, we define the spinel angle, which is the ratio between the spin current generated and the total electrical current injected into the heavy metal. Skyrmions have been received a lot of attention, especially because they were proposed to be used in racetrack memories. In the standard concept of racetrack memory sees the Skyrmion as coding the bit 1, while the absence of Skyrmions coding the bit 0. But today we can have a different concept of racetrack memory, such as bilane racetrack or coding in different topological textures. What is important that the racetrack memory is fully electrical. And we gave our contribution to this field a few years ago, where we studied the different scenarios where we can build a racetrack memory based on the type of Skyrmion and on the motion source. And also we developed an analytical formalist based on the TL equation, where we can see that the Skyrmion motion is not straight along the electrical current, but there is a phenomenon called Skyrmion effect, where the Skyrmion move with a finite in plane angle, which is called Skyrmional angle. And after the first theoretical prediction, the Skyrmion motion was also experimentally observed, but in different systems, as we see here, and from different groups worldwide. So the results are very well established. And in particular, we saw that realistically, Skyrmions are not affected by pinning as the theoretical prediction, but they are affected. And in fact, we see here there is always a threshold current to initiate the motion. And also, the experiments show the finite Skyrmional angle, which is undesirable if we want to use Skyrmions in shifted dynamics, because Skyrmions will inevitably meet the boundary of the system and be annihilated. So after this first observation, there was a search for finding a solution to this issue. And one solution, one strategy is to use the synthetic antiferromagnets. These have been proposed firstly for the domain wall motion by the group of Stewart Parkin, where they achieved the record velocity, this record velocity. And basically we have two ferromagnetic layers separated by a non-magnetic spacer, which are coupled to this interlake exchange coupling. After that, also the Skyrmion motion was analyzed in SAF, and in particular, we observed that in this system, the Skyrmion angle is suppressed if the interlake exchange coupling is sufficiently large, but also that we can achieve very high velocity approaching the kilometer per second. Also in this field, we gave our contribution, and we showed that in the static case, in order to obtain Skyrmions, at least with the parameter of the Stewart parking paper, we need two Jaronski scheme interaction for the two ferromagnetic layers, and in particular, these values must be opposite in sign in order to have an anti-parallel alignment. And to achieve these results, we need to use, for instance, we suggest to use platinum and tungsten. Dynamically, we also show that in synthetic antiferromagnet, the velocity of Skyrmion is much closer to the one of the domain wall than the case of single ferromagnetic layer, where the velocity of domain wall is at least 3 times larger than the one of Skyrmions. In any case, for both domain wall and Skyrmions, if we want to improve the mobility, we need to inject two current density in the two heavy metals, but with opposite spin-on angle. And again, the choice is platinum and tungsten. Recently, the first SAF Skyrmions were observed, and in particular, I want to point out that in this experimental paper, they use tungsten and platinum as our theoretical suggestion, and also they show these velocity current relation. On one hand, these results is promising because in SAF, the Skyrmion velocity is at least 5-6 times more larger than the one in the single ferromagnetic layer. However, in magnitude, this velocity is still very low because it does not achieve even 10 meters per second. So for sure, we need a lot of improvements experimentally to achieve the theoretical prediction. Maybe a solution can be this different system proposed by the group of Professor Fert, where they still observed the SAF Skyrmions as we see here, but we are still waiting for the current-driven dynamics. Another strategy can be the use of ferrimagnets, but we won't focus on this for this talk. And the last choice is the use of antiferromagnets, and in particular, Antiferromagnetic Spintronics have been receiving a new attention in the past few years, because nowadays we are able to control the antiferromagnetic order via spin polarized current differently from 50 years ago, and also we are able to image the antiferromagnetic order more easily than the past. And of course, we are interested in antiferromagnets also technologically, for instance, because of the terahertz dynamics. The Skyrmion motion antiferromagnets was proposed a few years ago, where we see that the velocity can again achieve the kilometer per second as the case of synthetic antiferromagnets, and also that the Skyrmion angle is suppressed. However, while we move the Skyrmion in this racetrack, we observe that as we increase its velocities, there is a lateral expansion in the direction perpendicular to the motion. And this expansion can be detrimental again for shifting application properties of the Skyrmion, because the Skyrmion will meet the boundary of the samples and be converted into a pair of domain walls. So our question was, is there a strategy that we can use to reduce or suppress this lateral expansion? And the answer was yes, and we can exploit the so-called topological torque that was introduced by the group of Professor Manchon. And in fact, we initiated a collaboration with this group, and we developed an analytical formulas as well as perform micromagnetic simulations, where we can include all the torque that we've seen before, therefore the spin orbit torque from the spinel effect, the spin transfer torque with its adiabatic and non-adiabatic terms, as well as the topological torque, which is proportional to the topological density of the topological texture in the antiferromagnet. This is also proportional to the current injected and to the parameter lambda. But now we can study the motion for the three distinctive torques. We know from the analytical formalism that we are able to calculate the expansion of the skyrmion along the x direction as well as the one along the perpendicular direction of the y direction compared to the equilibrium skyrmion sides. And therefore, let's start from the spin orbit torque, from the spinel effect. We see that analytically we expect a saturation of the velocity when it's approaching the spin wave velocity Vm. And also this is proportional to the equilibrium skyrmion sides, meaning that the bigger is the skyrmion, the larger is the expected velocity. We perform the macromagnetic simulations, and we see here that the analytical prediction is linear. The velocity is linear as a function of current, dashed line here, but the macromagnetic simulation indeed predict a nonlinear behavior for larger currents. This is because the skyrmion exhibits this lateral expansion, so becomes bigger, but this expansion is not taken into account into the velocity. Now we can move to the spin transfer torque. In this case, we expect a linear velocity with current if we fix beta and alpha, so the non-adiabatic parameter, the damping. And in fact, we see that now the matching between the macromagnetic simulation and still the analytical is excellent. However, there's the vector plot of the simulation still show a lateral expansion of the skyrmion, because this is an intrinsic property of a traveling soliton in antiferromagnet. But the spin transfer torque velocity does not depend on this expansion. Also, I would like to point out that for both spinel effect and spin transfer torque, the expansion as a function of current is abrupt, I will see here, and basically is quadratic with current. Finally, we can study the topological torque effect, and we see here a small difference with the previous cases, because here the dependence on the sides is at the denominator. So we expect the topological torque to be stronger for smaller skyrmions. But on the other hand, we know that the skyrmion moving in an antiferromagnet tends to expand in the direction perpendicular to the motion. So we have to deal with this trade-off, and therefore we expect that the velocity saturates at the smaller currents. Indeed, if we work out this equation for velocity closer to the spin wave velocity, we see that this should saturate for a velocity equal to 1/8 the spin wave 1. Therefore, we perform the macromagnetic simulations, and we see that, in fact, the saturation occurs at smaller current density, but we also observe that the expansion along the lateral dimension is linear now with current and no longer quadratic, and this means that the expansion is reduced. So thanks to the topological torque, we are able to somehow delay the lateral expansion of the skyrmion by keeping the same high velocities of the characteristic of the antiferromagnets. And as a perspective, this year we have seen the direct observation of the hematite antiferromagnet with PIM. So we don't need anymore an imprinting technique. And in particular here, they observe some half skyrmions and merons. So this study is promising also for the stabilization and observation of skyrmions in antiferromagnet. I would like also to point out an important feature of skyrmions over, for instance, domain walls. That is the possibility to move when the motion is characterized by a zero skyrmion angle, to move skyrmions through interconnected breeds. And this is not possible to be achieved, for instance, in ferromagnet, where we have a finite skyrmion angle. And therefore, antiferromagnets and synthetic ferromagnets are promising for this reason over domain walls, and therefore also for unconventional computing applications. These are my conclusions, and I would like at this point to thank the Spintronic group in Italy where I work, as well as the project Thundersky, which funded this research. And of course, I would like to thank all of you for your kind attention.